Here at QA1, we make suspension products, driveline products, and rod ends for motorsports and industrial OE applications. Today we're going to talk about the design and manufacturing process of our GM upper and lower control arms.
We always try to understand who our target customer is for this project and think about what sort of problems are they trying to solve, and how can we help them solve that. We spend a lot of time interacting with customers, and that's our #1 source of information on where we should go next for our products. So we're expecting more out of cars than when they originally rolled off the line in Detroit. We know that our customers have different demands. The Control Arm 2.0 project, we realized that the original design of these control arms was tailored more towards a conventional spring, but we have so many customers that want to take advantage of the versatility of a coilover setup, so we knew that we needed to design around that. We decided it was time to just start over from the ground up. What can we do better? Make them lighter, make them stronger, use a more compact footprint that will allow for more clearance, tighter turning radiuses, modern wheel and tire packages.
Once we identified the problems to solve, we started the design process. Our in-house prototype process starts with a CAD design, and from there, we rapid prototype parts on a 3D printer, and we do test fits on the vehicle. And then once we feel like we have a good design that we like, then after that, we'll make metal prototypes to fit in the vehicles. So a few design features that we incorporated into our QA1 control arms are a stamped steel lower control arm mount. It's a drawn piece of steel that helps with weight, also helps with strength. You don't see it a lot on control arms for applications like this. And another thing we also did was a forged one-piece ball joint housing, and that allows us to reduce weight, increase strength, and helps with repeatability in the manufacturing process. We also looked at tube angles, tube bends, where they need to be, how they need to come together, so that we can better utilize our robotic welder for our manufacturing process. Once those things are all locked in and designed in, then we move on to validation and testing.
In order to simulate real-world testing, we like to use our TUV dyno and our strength tester to actually verify when something is going to break, when something might fail before we ever put a part on a car. On our dyno, we can actually simulate the worst case scenarios. So like we can take a part and basically simulate what it would be like hitting a large pothole, but not just a few times driving down a road, but hundreds of thousands of times. With our strength tester, we can find what the ultimate strength of a part is, so we can actually test it to its breaking point and find out where the part will actually fail. A lot of the employee cars that we use are fellow engineers, and so when they're out driving these cars every day, they know what to look for, and the average person that's driving these cars may not. And so we can get that feedback right away that especially if there is a problem, we can immediately fix it. With our test partners, they don't know the engineering necessarily that went into the part. When they install it, they're gonna be like most anybody else that's installing it in their garage. And when they're driving down the road, they're gonna be able to more tell us what they heard, what they felt, and not necessarily give us an opinion on what they think might be wrong. One of the things that I'm most proud of when it comes to the design of these control arms is the fact that they're not like anybody else's. I mean, they don't look like they're just a bunch of tubes that a guy in his garage welded together and threw these together. I mean, these are precision engineered parts that have a specific job, and they are designed to do their job well.
We ensure a high quality product by starting with good materials and components at the start. We also have various check fixtures and check process all throughout the manufacturing process. And then when the part comes together and gets assembled, we have an assembly cell, a dedicated station to help minimize errors and ensure a really consistent and repeatable product. We verify accuracy with a lot of different fixtures throughout the control arm manufacturing process. We have fixtures for incoming parts, so we have fixtures that check incoming parts, make sure they're to the proper dimensions. We also have fixtures that happen while the product's being welded. For our control arm project, we did a lot of work on the packaging and decided to come up with a new way to package our control arms. We have a dedicated box and insert for both our uppers and our lowers, and we took a really hard look at how the part's held, how it's presented, make sure things get to the customer without dings or scratches. These products are all brand new, and those are developed throughout this process, and we're using them in these and future products as well. Thanks for taking the time to check out how we manufacture our control arms. We do a lot of work to make sure that we get quality product out, and be sure to check us out at QA1.net and also our social media channels.